session of mixed signal IC design. In today's class, we will look at few ADC architectures what we have. So, if you look at the trends, especially the market trends, you will see that there are various architectures rules the market for analog to digital converters, and among that, even if you classify ADCs, we can classify it as basically it as two, one under Nyquist rate ADC and one under oversampling ADC. So for our course, we'll be looking at the architectures of a few form of architectures. One is we will look at Flash ADC. Another one is we look at pipeline ADC. Then we will have a detailed study about successive approximation register SAR ADC, and also we look at oversampling ADCs. Alright, these are the four types of ADCs what we will be dealing in this course. So let's start with the Flash ADC. Let's start with this form of ADC. So out of all the ADCs what I have listed, this Flash ADC has the highest speed. So that is one very important feature of this Flash ADC. This is actually having the highest speed among all the mentioned ADCs. Alright. Now in contrast to the other types of ADCs, what we have here is we use a string of resistors. As in a resistor string DAC, we use a string of resistors, and also we use comparators actually to perform comparison per quantization level. Alright, so what we do is we will quickly look at the architecture of this and how it works. We'll see in sequence. So as you know, in an ADC you will have an input voltage, and we need to compare the input voltage with the reference voltage, right? So the reference voltage will be generated with the help of a resistor string of resistors. So if you have VREF as here, we will be having a string of resistors in order to generate the reference voltages. Maybe if you connect like this, say for an n-bit ADC, so for n-bit ADC, what we'll have will be 2 to the power of n resistors. Right, that is what we'll have, and similarly for each quantization. So all these are same value resistors. We'll be using same equal value resistors for all these, and we'll have 2 to the power of n resistors. All right. Now, so at every point, from every point you will have a reference voltage which is generated. Now this will be compared with the input voltage, right? That means for comparison purpose we will have comparators here. So we will have comparators for the comparison purpose, and let me put this as minus plus. To the minus input terminal, the reference voltage will come through the resistor string, and to the plus input we will have your input voltage. So input voltage will be connected to the plus input terminal directly to all the comparators. So this is your input voltage. Vin will come at this point, right? Now if you look at this architecture, as you can see, the reference voltage is divided into 2 to the power of n values, right? And each is actually fed into the comparator. As you can see, from every point it will be fed to the comparator. Now input voltage what we have given here at this point is compared with each reference value. So the reference value for each comparator is different, because reference value here at this point, at this point, at this point, all these points, reference values are different. So the input voltage is compared with each reference value, and that will actually result in a some code at this point. So as a result of this comparison, comparator will actually produce some output, right? Now the kind of output, so what we get here is say for example, if your input voltage is I'll take an example and we'll look at in details how this ADC is performing comparison and generating code. But in general, what we observe here is at this point, the result of this comparator is basically what we get is in the form of a thermometer code. We get in the form of a thermometer code, and for that reason, soon after this stage, we have to include some decoder, because what we are getting here is thermometer based code, which like how many values you will get, 2 to the power of n minus 1 you will have. But what I need is for an n bit ADC, what we are expecting is an n bit output, right? So we need actually a decoder of 2 to the power of n minus 1 is to n. This type of decoder is required here, so that we will get output at these points, right? So if I mark the output, I can mark it as D0, D1, D2. So this will be Dn minus 1, this is Dn minus 2, this is Dn minus 3. In general, we can write like this. So this is the digital output what we will get, right? So this is the overall architecture. So we'll have a string of resistors, equal value resistors, which will generate different reference voltages, fraction of reference voltages, and that reference voltage along with the input will go to a comparator. Comparator will perform comparison, will generate a thermometer code, and that code will be decoded from 2 to the power of n minus 1 to n decoder, and that will give you the digital output, right? So what happens here is the thermometer code what we'll get here, that will actually exhibit all zeros for every resistor level if the value of input voltage is lesser than the value, right? The value of the input is less than the value on the resistor string, it will give you a 0. Otherwise, the value will be 1. We'll see that. So we'll see how this portion work, or what we will actually get at this point. We will see in detail by taking an example, right? Now, so now the question comes, why flash ADC, or why this is popular? So the very important advantage of this flash ADC is in every clock pulse, this can actually generate an output digital word, because you can see that here we are using one comparator per quantization level. That also I need to mention here. One comparator per quantization level. Alright. So when you say one comparator per quantization level is actually a huge number, right? The very important advantage of this is output digital word is generated. Output digital word is generated at every clock pulse. Alright. So we know that none of the architectures will come without any drawbacks, right? Because you can see the need of comparators here is huge. That will definitely result in the area more like huge area. Also, we need more power actually to drive all these comparators. So those things are the additional things. Say for example, let me take, if I am looking for an 8-bit flash ADC, flash ADC, the number of comparator requirement is 2 to the power of 8 minus 1, which is equal to 255. So I need to find space to accommodate 255 comparators to actually convert your analog data into digital. Similarly, if you keep on increasing this, if this is 9-bit flash ADC, then the requirement is 2 to the power of 9 minus 1, which is again another 511 comparators. But it is not a joke, right? For including many number of comparators together onto an integrated circuit is actually a challenge in terms of area, in terms of power, right? Now, for these reasons, typically we'll limit, or the use of flash ADC is generally limited up to 8 bits in CMOS architectures, but there are again that depends on the requirement what we have, right? So this is in general about the architecture of flash ADC. What we have will be a resistor string, comparators, and a decoder circuit, right? Now what we'll do is we'll take a typical example of a 3-bit flash ADC. We look at design of a 3-bit flash ADC, and we'll exactly see how these thermometer codes are generated and how we are actually getting the final value, right? So now the very first thing is, we know that the number of bit is 3, n is equal to 3. That will actually give you two things. One is you will know the number of comparator requirement 2 to the power of n minus 1, which is 2 cube, 8 minus 1, which is 7 comparators. This is one of my primary need. I need to have 7 comparators. Second thing is n is equal to 3, you need 2 to the power of n resistors. Equal value resistors, 2 to the power of 3 is 8. 8 resistors we need. Right. So with this in mind, you can actually go ahead and draw the architecture, right? So when you draw the architecture, yeah, these things should be kept in mind. Let us, from the architecture what we have discussed, what we know is we'll have a reference voltage, and the reference voltage should be divided equally among, not equally, reference voltage will be divided with the help of this resistor string. 4, 6, 7 and 8. These are 8 resistors, right? All of same value R. Right. Now, from each point of this resistor, we need to connect a comparator. So a comparator need to be connected here. All right. So the polarity of the comparator, it can be the other way. The only difference is, the thermometer code will come in the other fashion, the reverse fashion. All right. Now to the other input of this comparator, what we need to give is the input voltage. So input voltage, say if the input voltage is available here, it can be directly connected to all these points like this. It can be connected to all these points so that we will get comparator output or the thermometer code at this point, right? So we can number, since we have how many, we have 7 comparators, right? So let me mark it as C1, C2, C3, C4, C5, C6 and C7. And one more thing what we need here is, since the code here is thermometer, we need to convert this into a digital code. So we need to use a decoder of 2 to the power of n minus 1 is to n decoder. And finally what we'll have here is a 3-bit output, where this is designated as D2, D1 and D0. This is how the Flash ADC looks, right? Now first, if you look at the voltage at each tap, see at these points, if you look at the voltage, we know there are 8 resistors. So yeah, if I number it, yeah, so let me write it here. Voltage at each tap of the resistor can be, if I am calling it as VI, if I am writing it as VI, I can write it as VI will be equal to the reference voltage into I divided by 8, right? Because we are the first voltage here will be full VREF that we are now taking. From here onwards we will have. So say for example, now here I will be varying from will be varied from 1 to 7, right? So if your I is 1, the value, the reference voltage VI, so when I is 1 at this point, so here the voltage will be equal to VREF divided by 8. Next point it will be 2 into VREF divided by 8, it is VREF by 4. So that way it will keep on increasing, right? So if you look at that, let me just create a table over here. Let me move this towards left. All right. Now, so what I need is, I need to know what is the input voltage range. Depending on that, what is the output I am getting as thermometer code, C7, C6, C5, C4, C3, C2, C1. And using decoder, how can I convert that into a digital code? This is what I am looking for, right? Now, if I look at this input voltage, So for every comparator, the comparison range is, see, look at this. Here the voltage, the available voltage will be Vref into, this is Vref into, Vref divided by 8. Say for example, I am keeping Vref as 5 volt. Right. If my Vref is 5, the reference voltage what I will get at this point is 0.625, which is Vref by 8. Right. Now at the next point here it will be 2 into Vref by 8, which is nothing but Vref by 4. Right. So which is equal to 1.25. Similarly, if I look at the voltage available at every node, I can write the voltages as 1.875, this is 2.5, this is 3.125, this is 3.75, and this is 4.375, and there comes the full scale voltage. No, full scale voltage will be, in this case, it will go up to 4.375, and the next one is 5, right? But anyway, we don't have, we have only 7 comparators here. Now this is how the voltage range. So now look at the architecture. So previously we have just seen the architecture. Now the comparator C1 is now responsible to compare, or the comparator C1 will actually produce a 1 when the other node, the minus of comparator C1 is at 0.625. Now if your input voltage is greater than 0.625, C1 will actually give you 1. Otherwise C1 will give you 0. Right. So how can I write that condition? That condition can be written as, if your input voltage, if it is less than or equal to 0, if it is in this range, so I'll write here less than 0.625. If this is the condition, right, what will happen if your input voltage is within this range? You will have, if it is less than 0.625, right? So if it is in this range, all the other comparators will definitely give you 0 only, right? Because you look at this, when your input voltage is within the range from 0.625 to 1.25, right? When it is more than that, the first comparator should give me a 1 output. So initially for this, all comparators will be at 0. When your input voltage is lesser than 0.625, since input is lesser than 0.625, your output will be actually at 0. Right. So correspondingly what I have is also 0. Now when your input voltage is between 0.625 and the next value, which is 1.25, right? If your input voltage is within this range, now you can say that comparator C1 is having, at one node it is having more than 0.625, but the minus of comparator C1 is still at 0.625, which will make your C1 to produce a 1 output. That means here you will get 1, but rest everything. Look at all the other comparators from C2 to C7. The plus is having a voltage which is less than 1.25, but minus is having either 1.25 or more. That means your output will be 0, right? So here all the output will be at 0 voltage. I hope this is clear, right? So look at the first case. I'll repeat. If your look at this. When your input voltage is less than 0.625, so here your input is less than 0.625, all comparators minus are either at 0.625 or at a greater voltage. That means automatically all the comparators will produce a 0 output because of the higher voltage at the negative input terminal, right? Now when it comes to the second case, in the range of 0.625 to 1.25, only for comparator C1 plus is having a higher voltage compared to minus. For all the other comparators it is at 0, right? So that will result in 0, 0, 1 here, and this will continue from 1.25 up to 1.875. You will the next comparator, right? So the next comparator C2 also will produce a 1. So this is why we call this as thermometer code, right? So for all the values higher than the input, it is actually giving you a 1. Lesser than input, it is actually giving you a 0, right? When your input is greater than the reference, you are getting 1. Otherwise, you are getting a 0. That is what is reflecting here. So this will result in 0, 1, 0. Similarly, we can write for the entire range. When your input voltage is less than 2.5 you will have 0, 1, 1. When your input voltage is 3.125, this will be 100. When your input voltage is 110, I think I missed something here. Yeah. This is 101. Now this is 110, and so this is in this range. Now for any input voltage from 4.375, input is less than this condition, right? We can write in this way only. When your input is less than this condition, we can say that for the last comparator, right? Because look at this, whenever your input is lesser than 4.375, sorry, yeah, this is 4.375. now if your input voltage is the input voltage here, if it is more than, right, if it is more than 4.375 only, you will have all these at 1, and that will result in 1, 1, 1. Yeah, the higher. Yeah, so this is how we can develop the transitions for this flash ADC, right? All right, so this is the very simple architecture what we have discussed. We have the thermometer code, and correspondingly using a decoder, actually you should get the corresponding digital output code, right? So this is about the architecture. Now quickly we'll also see how much this accuracy issues will affect this flash ADC. Let us quickly look at that, right? So so there are several things comes into picture. The one important thing is we are using a string of resistors, right? So as we have discussed in resistor string DAC, the matching of resistor string is very, very important, or the accuracy depends on that too, matching of the resistors. And if you remember, in resistor string DAC we have considered mismatches in different ways, right? We considered that for the lower half you have positive mismatch, the upper half negative mismatch, so the middle point will be a point where you will have so those things we have considered. So we'll do this in the same line what we have done over there. So one thing is it depends on the matching of resistors. That is very important. Matching of resistor string is important. That is one thing. And another thing is, since you have comparator, we should also have a look at the input offset voltage of the comparator. Right, input offset voltage of the comparator. All right, so yeah, so what we'll do is yeah, so let me I'll be taking the equations what we have looked at in the case of resistor string DAC. So say voltage on the ith tap of resistor string, we can write it as, say if it is Vi, we expect there is an ideal voltage, plus now I need to include the mismatches as well. So I'll include mismatch as Vref divided by 2 to the power of n into summation k equal to 1 to I delta Rk by R for the entire for the full string, right? Now yeah, so what I meant here by Vi ideal is assuming that all the resistors are equal and ideal, right? Now let me mark those things as well. So this is delta Rk is basically the resistance error, due to mismatches. This component is when everything is ideal and R are equal, R values are equal. Right. Now, one more. So this is from the, as I mentioned, for accuracy issues, we need to consider two things. One is matching of resistor string. So the same equations what we have dealt before I have directly taken. Now coming to the offset voltage of the comparator. So generally for an ideal op amp, we know that so whenever maybe if there are two voltages, V plus and V minus, whenever the voltage crosses, immediately output should switch. But we know that offset voltage will be there, and that will actually prohibit, or it will prevent the comparator to switch from one level to another level. So in general, what we look for a comparator is your output will be equal to 1 if your voltage at plus terminal is greater than minus terminal, and voltage will be equal to 0 if your V plus is less than V minus. But now we need to add a offset component here. So when your V plus is greater than V minus plus this offset voltage, here also I'll add that offset voltage, right? So an offset voltage will come into picture, which will actually introduce some kind of accuracy issues. So keeping this in mind, if I write the equation, now I need to write the switching point. Say for example, now the switching point for the ith comparator can be written as, switching point for the ith comparator should be now written as Vi, which is the ideal value, plus I need to include the offset voltage as well. These are the two things this is first thing, one thing we are considering it as new compared to the resistor string DAC, right? Where what is this V offset of I? This component is nothing but the input referred offset voltage. Alright, now what are we trying to do with by writing all this accuracy related thing? We are actually going to calculate the INL, integral nonlinearity. And how can I calculate that now? V switch of ideal for ith tap, V switch of the exact value minus the ideal value, right? Which can also be written as V switch I minus the input voltage at the ideal. Either way we can write. So when I write the equation for this, what we can do is INL can be written as, we have already written the equation, so we have to subtract it. So it will come as Vref divided by 2 to the power of n summation k is equal to 1 to I delta Rk divided by R plus the offset voltage, right? Because INL is basically the difference of these two things. So the difference of these two is nothing but Vref divided by 2 to the power n summation k equal 1 to I, plus we need to add the offset voltage, V offset of I. That is what I have done here in this equation, right? Now in similar to what we have done in resistor string DAC, I can actually go for a worst case INL calculation, and I am assuming that occurs at the middle of the string, assuming that the lower half will have positive mismatch and upper half will have negative mismatch. And I hope you remember we have discussed these things in little more detail while considering resistor string DAC. So middle of string, and the middle of string point is nothing but when I is equal to 2 to the power of n minus 1, right? So here I can write the maximum INL max as Vref divided by 2 to the power of n into summation k equal to 1 to 2 to the power of n minus 1 delta Rk divided by R, plus I need to also include the offset voltage as the maximum offset voltage value, right? So this can be further simplified by taking all these things as Vref into 2 to the power of n minus 1 divided by 2 to the power of n into this R, and I'll write this delta Rk maximum value here plus the offset voltage maximum, right? So with this I can write INL max as, this is nothing but Vref divided by 2 into delta Rk by R plus V offset maximum. Right. So again, this is based on the assumption that maximum positive mismatch is happening in the lower half and maximum negative mismatch is happening in the upper half. Alright. So this is all about a brief introduction about Flash ADC. The main thing is the advantage of this Flash ADC. For an n-bit ADC, how many comparators, how many resistors we need, and how do we convert thermometer to the digital code, and how we will actually get this code transition table. This is important, and also we should know for accuracy issues there are two things to be considered. One is matching of resistor string, and second thing is the input offset voltage of the comparator. Right. So with this I am winding up this session. We'll look at the other ADCs in the upcoming lectures. Thank you.